Since I started this late, I started the recording late, just real quickly, we are looking at our new R2.2, which is kinetics, rates of reaction unit. And we just talked about how the reaction rate is typically we measure in terms of concentration because most of our reactions are done in solution. So change in concentration of reactants or products per unit time. So we can either talk about an increase in products per time or a decrease in reactants per time. So that is pretty much what our how we're going to calculate rate. And as Jocelyn mentioned, this is basically looks like the slope of a graph, and we'll come to that back to that in a minute. So what I was just asking folks to do was to think about how they might sketch these graphs of a change in concentration versus time. Number one, what the reactant concentration would look like over time, and number two, the product concentration. So we have a couple of suggestions of how the product concentration graph might look, the shape of that graph. Certainly starting at 0 makes sense. Anybody else want to come up and offer a thought on either of these? I mean, we've got nothing for number one right now. Okay, so full on linear. Alex? Oh, yeah. Here, I'll give you a bunch. That's all right. Okay. Reactants starting at some point and then decreasing. Anyone else want to add something to either of these? Okay, so we've got a decrease that sort of starts off faster and then slows down. Okay, yeah, these are all good thoughts, and I don't expect you to have the right answer magically in your head, but you can see that there's a lot of different ways that we could see something like this unfold. There is a right answer to this for most conditions. Now, depending on the conditions, you're going to get different shapes of an actual graph that you're collecting data from in an experiment, okay? But sort of the canonical way of looking at this is actually going to be the inverse of this blue line. So we are going to start our products at 0, because presumably, until we get to the next unit, actually, presumably we're starting with our reactants and we're making our products. And so what's actually going to happen is it's going to start off pretty quick. And then it's going to slow down over time until we reach that tail off point, that end point. So that sort of flat line at the top is absolutely correct. But it's actually going to go faster at the beginning. So a little bit, the reactant graph is going to be a little bit more like the green line here, in that it's going to start off fast and then slow down. And then theoretically, could be, if the reaction goes to completion, we'd eventually get to 0. Reactants, all the reactants would convert into the products. If the reaction doesn't go to completion, then we might tail off at a space other than 0, kind of like the green line did that Luca drew. Okay, so the black line is sort of what typically tends to happen. Why would it start off faster and then slow down? We're going to answer this question later, but I want you to think about it. Alex? Yeah. So at the beginning of the reaction, all we have is reactants. Every particle in our system is a reactant particle. And they're coming together and they're making the products. As we continue the reaction, that slope is going to get shallower, whether it's this slope or this slope, because we are running out of our reactants. So there's just less of it around. There's going to be, it's going to be slower to find each other. And we'll talk more about that later. So I'm just going to wait. But these were all good ideas. And, you know, connects to the basics of this correctly. So we'll talk a little bit more about why that curve happens in a little bit. Okay, so here's our graphs. Like Jocelyn said, our time is always going to be on the x-axis. Our concentration, or whatever it is that we're measuring for the reaction rate, and you'll get to see that there's lots of ways to measure even the exact same reaction. But if we're just looking at concentration, we're going to have that on the y-axis. And so our concentration is going to be in moles per decimeter cubed. Time is going to be in seconds. Now that's, if you're running an experiment where your reaction takes longer, your time might be in minutes. Hopefully, if you're doing an IA, your time isn't in hours, because it's going to be a very long slog for you. But there's two ways that we can use the graph. One way is to find this instantaneous rate of reaction, and another is the average rate of reaction. So let's talk about the instantaneous rate first. So instantaneous rate is the rate at any particular time, at any moment during the reaction. And the way that we're going to look at that is by drawing a tangent line to the curve. Okay, so this is going to be, oops, let me make that not black. Okay, and then you find the slope of the tangent line. And hopefully you can see that over time, that tangent line, and I can't really do this well because I can't put a ruler on the board, but that rate, that slope, is going to get shallower. The rate is going to decrease as we go through the reaction. That's a terrible line. Let me read you that one. Okay, so that slope is going to decrease as the reaction continues, but we can find the rate of reaction at any particular time. Okay, the most common thing to do with this is to find the rate of reaction at the very beginning. Okay, what we call the initial rate. So that's why that's drawn on your study guide. So this would be essentially, oops. This would be initial rate. Right at the beginning of the reaction. And that should be the steepest slope. Okay, so that's often used as one measure of reaction rate, is just the rate at the beginning. There are a number of reasons to use that. One of which is that you don't have to let the reaction run for very long before you get to measure the initial rate, right? You only have to run it for a few seconds, and then you've got that tangent line. But also, that's going to be our highest rate if we're looking at it over time. Okay. Okay. Oh, sorry, I forgot that this was a separate slide. So yeah, you're going to draw a tangent to the curve at a particular time, time 0 for the initial rate. And then you're just going to measure the slope of the line. They use the word gradient. I think it's a British thing rather than slope. Gradient equals slope. Okay. And again, because we're doing y over x, it's going to be, the units are going to be in moles per decimeter cubed per second, right? To find the average rate across a certain period of time, like say you're going to run your reaction for 30 seconds. And in all of your different conditions, you're going to run it for 30 seconds and then stop, and you're going to find out what was the average rate of reaction across those entire 30 seconds. Okay, so that is where you basically just pick a point on the line and use the coordinates, y over x, right? Or if you're picking a spot in between, like in the middle, like maybe you want to take the second 30 seconds of the reaction for some reason, you would start it at 30 seconds going to 60 seconds and then find the difference in y from there. So this is also the kind of thing that if you weren't taking data over time, if all you did was have an endpoint for your reaction, like when it stops bubbling or when it changes color or something like that, this is the only data you would get. You wouldn't be able to track it over time, but you would be able to calculate an average rate of reaction. There are certain reactions, and we'll probably do one of these. I'll at least demo it, if not have you do it, called clock reactions, where you mix the reactants and it takes a certain amount of time, and then all of a sudden, boom, it changes color. And so that's the kind of thing where you can't see what's happening in between. All you can see is the point at which it tips over into the other color. So this is useful. It's not as useful. You can't do as much with it as you can if you are collecting data continuously over time. Okay? But it's still, you can still get reaction rate data from this kind of thing. All right, so question 4. I'm going to throw some rulers out here and you guys can share them. Your task is to determine 2 things. So you're going to make 2 calculations. The rate, the instantaneous rate at 40 seconds. And then the average rate between 0 and 60. Here, you guys can share one. Share. You guys can share. You guys can share. Maybe I have enough, actually. No, I don't think I have quite enough. Oh, you have one. Good. I think your socks. That's exactly what you do. I'm sorry. So guys, the tangent line for the instantaneous is going to be a straight line that touches the curve at that point. Okay, so that's what a tangent is. So if I was drawing a tangent line at 90 seconds, again, I can't do it well on the board, but it would be something like that. That's actually a terrible line. Let me try it again. something like that, okay, where if it touches the line and I'm getting the slope of the curve at that particular point. So that's what a tangent line would be. And when you're doing it by hand, everyone's line is going to be a little bit different, and that's okay. You're going to have a little bit of a range of values here. Calculators. Calculators. Calculador. Calculators. 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 Is it gonna, oh, damn it. All right. Of course it would glitch on me.